So, hello, first of all, I'm Brigante. You can find me on Twitter, Facebook, Instagram. I don't know what would you like my Instagram, if you wish. I'm here to talk about Immutable.js. First of all, sorry, I'm a bit sick, so I'm a bit coughing a lot, so sorry about it. But today we're going to talk about Immutable.js, and it's kind of a spoiler, right? Because as soon as we talk about immutability, we assume that we are going to talk about immutable data structures against mutable data structures, right? If you wouldn't know him, is Dorian Gray from that movie. Just someone saw that. But it's the only character that I found that represents the immutable things. And the case that it's a female is nothing to do with sexist things and stuff, so it's just the mutant. But the important thing here is to understand what are the principles behind mutable data structures. So it will be, they are easy to use, right? They are familiar for all of us, I guess, right? Like objects and arrays that we are all used to work with them. DOM elements, they are also mutable structures. They are super efficient with large amounts of data. That's why we see that mutable structures all over the place, because we tend to deal with large amounts of data. We can see mutable objects in JavaScript, or a couple of new things coming to JavaScript from mutable data structure as the mutation observer API. It is a new API that allows you to observe, to be notified every time that a DOM element changes. So every mutation on a DOM element, you can see it, you can be notified. There is also a new function in JavaScript, which is object.observed, which allows you to do that with a plain JavaScript object. So you can be notified for every change there. It's quite interesting. It allows you to create proxy and a lot of kind of stuff. But we're going to see that this is bad. It's not that good, right? In the other side, we have immutable data structures. For immutable data structures, we have a couple of things here. They are more simple to understand, I would say. They are like values, common values. I don't know, integers or booleans. Those are immutable data structures. Strings, for example, are immutable. Until recently, we had a couple of languages with mutable strings. They were super awful there because they were super error prone. For example, if you're creating a hash table and you hash an element with a string and then you mutate the string, you cannot use the same object to get that key because the hash value of the mutated string is going to be another different value, right? So mutable string, we don't use it. Immutable data is also super safe for multi-thread programming, which is really interesting because in the future we're going to see, well, we are actually starting to see a couple of libraries in JavaScript that are bringing the multi-thread world into JavaScript. There are a couple of operations that can call native platform directly in the chip. Intel is an Intel API. I can't recall the name right now, but with one instruction, it allows you to multiply vectors and arrays and stuff. So multi-threading is coming to JavaScript. Immutable data structures are super safe for multi-threading programming. And they are also coming into the JavaScript world with React. I don't know how many of you have ever used React here. Okay, we have a couple there. Okay, nice. So in React, whenever we're trying to change the state, we cannot mutate the objects in the state. We have to create a new one, right? So those are, I would say, it is an immutable interface that is required by React. They don't provide the immutable data structure, they require an immutable data structure. So that's why Immutable.js is coming from Facebook, because it fits perfectly into React world. Also, it's happening the same with Redux, right? Whenever we are trying to change or modify a Redux store, we need to create a new object instead of mutating the existing one. And of course, the most important example of immutable data structures in JavaScript, it's going to be Immutable.js. So, wrapping a bit here, it is about simple against easy. And one important thing that I want to mention here is that simplicity matters. And simplicity matters because the simplicity is a property that we tend to not to give so much attention to it, and it's going to profoundly affect our day-to-day work. I strongly recommend you to check out this video by Rich Hickey. He's the inventor of Clojure programming language, and most of these ideas, even React, Redux, and Immutable.js are coming from the immutable data structures from Clojure. So, what's simplicity? Well, it's in terms of the definition. We're going to see the definition of easiness against simplicity. So first, easy. Easy is something that lies near, right? It's at hand. It is familiar to you. Something that you already know. That might be easy. In contrast to hard. But what's the problem with easiness? It is relative, right? Something might be easy for me because of who I am and where I came from, and something might be hard from you for who you are and where you came from. Instead, simplicity is like one fold, one braid. It's like twisting something, but just once. It is contrast to complex, and this is important. It is subjective. It doesn't matter who I am. Something, it's going to remain simple. If it's simple, it's going to remain simple. Simplicity is a prerequisite for reliability. Dijkstra. It looks like sometimes Dijkstra was only quoting things, right? It's always a quote from Dijkstra. But there is another word in English which is really interesting. It's complect. It is about complecting things, like folding, breaking things. We can say that simplicity is the contrary of complecting things. If I show you, whoa, there it is. Not yet, yeah, done. If I show you this and I told you this is A, B, C, and D, and now paint A and C in one color, this is simple to do, right? It's a simple task. Now if I show you this and told you paint C and D of color red, it is going to be much more complicated. So that's complecting things. Now let's see this with a clear example. Here we have an array X of 0, 1, 2, and then we have Y, which is a slice from 0 to 1 and a splice from 0 to 1. Of course, the value of Y is going to be an array with the element 0. What is going to be the value of X in this case? Who knows that? Okay, it's not a test, don't worry. The thing here, I'm not going to push you into a test here. Maybe a couple of us need to go to the reference. These two methods are not quite used anymore, but the thing here is that X is going to remain equal if I use a slice, because it is a method that operates without mutating the array. A splice, in the other case, is one of the fewer methods that mutates the array. So the value of X is going to be mutated. And I wanted to show you this example because what will happen if later I just want to define C, base it again in calling the same method 0, 1, right? Now C in this case is going to be 0 because X is still 0, 1, 2, and in this case C is going to be 1. Sorry. I'm gonna need another one, this one. So now what we can say here is this is simple because this sentence here has nothing to do with this one here, right? Instead, these ones are tied together. They're braided, right? They're mixing, they're compacting. So this is a nice word because when someone does something like this in your project, you can say you're compacting things, right? You're doing something wrong. So think about this. If you have this is your software, the software that you're writing, and then your boss come in and say, oh, please, could you change this line here? And you can say, oh my God, this is compacting with all of the other piece of code. So when you bring that line, you're going to find a lot of note, right? There's everything there, just read and fold it together, and you need to modify a lot of lines in order to make just one change. Typical that Moses always thinks that everything is simple, but this is the reason that something is complected into our software. So this is again why we say that some language features might give you enough rope to hang yourself. Good, right? So let's come back to Immutable.js. So now we have an understanding on these differences between immutable data structures and mutable data structures, the simplicity that they bring to the table, but we might need to trade off from the easy of use or from the familiarity of use. However, Immutable.js, okay, there it is. Immutable.js is the best combination of both. It's going to bring the simplicity from the immutable data structures and the effectiveness of mutable data structures, because it's going to provide us, well, it's exactly that. It's going to provide us an easy and familiar interface, right, for the objects, the things that we're used to, like objects and array, and under the hood it's going to be immutable. So it's going to be, come on, the best of both worlds. And isn't that awesome? Well, I hope it's going to be. This is an example here. This is how we use a list from Immutable. So I'm going to create a list based on a JavaScript simple array, right? And in this case, I'm going to have a list of 1, 2, 3. Now, if I push a new element, the element 4, then my list, it's not going to mutate. It's going to remain the same. But the push method is going to return a new array with the element 4, right? So both lists are going to be different. Okay, so how does push works? Of course, push works in the only way that we might think. It just receives a new body, creates a copy of the original list, then modifies that copy and then return the copy. So everything is going to be a copy of a copy of a copy. But isn't this going to create a lot of objects into our memory? Is this not going to be super slow? Well, probably, but it's again a problem of interface versus implementation, right? And we saw this problem before. We saw it with React. Essentially, with React, we're re-rendering all our UI every time that something changes. And that could be super dead slow, but it's not because of the implementation using the virtual DOM. So how we are going to fix that here? On implementation. Implementation here is the key on how it works. I see the resemblance there. It was super hard to find those keys. So, what Immutable does, Immutable uses persistent immutable data structures. And in this case, persistent means that every copy might be saved, or we're going to have a copy for a reference for every copy that we do of the particular data structure. And immutable means that every copy that we have, it's going to be immutable, right? We're going to mutate a copy, and once we return the copy, that copy is immutable. And how does Immutable does that? Well, simple, but using a property called structural sharing on directed acyclic graph. So this is super clear, right? That essentially, what a directed acyclic graph is just a graph. Remember that kind of tree that you did in college? Well, something like that. Imagine like this structure is directed because they have a pointer to their children, sorry. That's why they are directed. They are acyclic because each node doesn't have a pointer to its parent. Just an important property. Well, it is a graph because it is graph theory there. So now imagine that we want to modify this particular node here. I don't know if you can see that. So this, there it is. So imagine that you want to modify that node there, but you cannot modify it, right? Because we're talking about immutable structures. So you create a copy and modify the copy, and point the copy again to the same children, to the same child in this case. And of course, you need to its parent to point him to. So we have to modify the parent, but we can't modify it because it's immutable. So we create a copy, and so forth. We create a copy until we get to the root, right? And then we create a copy. Now, if you take a look at this, we have a complete new structure there for our new object, but we still have the other object, right? You see, if we maintain a reference to this root, we're going to have both persistent. If we lose the reference from that one, maybe in the future the garbage collector is going to get rid of that. However, the structure sharing part is because more than the 50% of the structure in this object is shared. So that is going to be efficient in memory print and in speed as well. So that's fine for trees, but we don't want trees. We want objects and arrays. Well, maybe not objects and array, maybe some more fancy structures like maps and lists, but it's kind of the same. So how do we implement maps and lists using these DAGs, this directed acyclic graph, using trees? This is a data structure called tree. It pronounced tree because it comes from retrieve. It's a fancy way of retrieving things. So here is an index tree. This is kind of the graph that we saw earlier, but instead of using nodes, it's used arrays. So let's see how it works. Let's try to get the value, the value 141, the index 141. So let's turn that into binary. It's 141 binary, and then we're going to take the most significant bits here, and we're going to start. So in the array we have there 0, 1, 1, 0. Then in the next hope we'll have 0, 0. And so forth. You get the idea, right? So this is essentially how to get there. And now we have this structure, the directed acyclic graph. So we can implement the structure sharing and share most of the structure in our list implemented inside Immutable. So this is the index tree. This is the structure that is used to implement list in Immutable. The same thing happens for hashes. We have a hash tree, which is kind of the index tree and has the array there, but now you can see that some nodes are leaf nodes. Instead of having another array, they have values. They don't have values, they have keys, and then pointing to the actual value. So how does it work? Well, like any hash, we first have to implement the hash function, which is going to receive a key, which could be any kind of object, and then it's going to be transferred into a number, into a 32 bits number to be accurate. So for example, if we hash the key R, the result is going to be 82. For a number, it's going to be the same number. So how does it work? Well, it's the same. So if we want to get the value inside the key R, we are going to hash the R. We're going to find that it's 82. 82 in binary is this one here. So we're going to do the same trick. But as you're going to see here, once we found 0, 1 here, we have only one leaf node. There we don't need another array because only have one value. There, right? You can imagine what would happen if I have several leaves that point to the same part. Well, we can just add another array here and then move the pointers, right? So it's going to grow with the same in the same way that I showed you earlier. So once I found the leaf node, I have to check if the key is the same, and then I could retrieve the value. And this is the structure that is used to implement maps. So coming again, we have maps and lists in the interfaces in Immutable.js, but in the implementation we have trees, right? Well, it's not like it's exactly the same than using arrays and objects, and let me show you why. Here's an example of a Immutable map. I'm importing map here. I'm assuming that we are working on ES6. So I'm importing map from Immutable, and I'm creating a new map. when I'm setting the RAM string to the R key, and if I try to get it, I receive undefined. Who could tell me why I'm receiving undefined instead of RAM? Sorry? Exactly. Because it is immutable. Map here is immutable, and here I created an empty map. So map, it's going to be an empty map always. So here, so stop trying to make it mutable. It's not going to mutate, right? So if we want this, we have to create a map like this. We have to create a new map, and then we're going to have a new map here, and to that new map, I'm going to set the RAM into the key R, and this is going to return a new map, which is going to be saved in the map variable. And now if I do the get R, I'm going to receive RAM. So for this, it's going to, we are going to have the same problem. If I try to reset the key with rock, and I'm executing get and R, I'm going to still receive RAM because map it's not modified. It is just returning a new map whenever I set a value. So if we want to do that correctly, we're going to have to store it on a second map, on a separate map. Okay. There it is. Now for list. This is the interface for creating list in Immutable.js. So it's just a list function. I forgot the uppercase there. So you create a list from an array, and then we are setting here the index 0, so I'm changing the 1 but with the value 8. So if I try to get the index 0 of the second list, I'm going to retrieve the 8. Now, list has an interesting quality that it provides the map, reduce, and a couple of other methods as well as array in order to let you operate on collections. So this is going to just return a new list with where every value of the list is going to be the same as before plus 1. In this case, the index 0 is going to be just 2. Now, take a look at this case, for example. Here I'm creating a list, an immutable list, based on an array of JavaScript plain objects, right? And then I get the object that is on the index 1, and I'm modifying the property p to be free. In this case, the object in index 1 is going to be this one, right? And when I get the value of p is 3. Why is this happening? Because I'm creating an immutable list of mutable objects. Don't do that. Don't do that. Just let go. We have enough of mutable objects. There is one of the videos of Rich Kiki. I recommend you to watch them all. One of the videos talking. We already knew that mutable data structures are bad. We knew that with strings. But however, we still think that arrays and objects are a good thing. And they're not. They're completing our software. So let's try to use more simple data structures. So don't do that. What we are going to do in that case, Immutable provides a function which is called from.js, which takes a JavaScript data structure and transform that into maps and lists based on if they are arrays or objects, right? And how do we operate on them? Well, just for example, using the update method, which is going to return, of course, every method returns a new version of the data structure. In this case, update is going to return a new list, where the index 1, which is this object here, it's going to receive an updater function. And that updated function receives as a parameter the current object, right? So here in item, I'm going to receive this object here. Well, I'm not going to receive that object specifically because I'm going to receive a map, an Immutable.js map. It is a version, an immutable version of that object. And then whatever this function returns, it's going to be stored in that index in the immutable list. So here, what I'm going to do, as item is a map, I can also use update on the map too. And I want to update the P property, or the P attribute in this case. And for P, it happens the same thing. It's receiving an updater function, and the updater function is going to receive as an argument the value, the current value of P. So in this case, P is going to be 2, but I just wanted to assign 3. So we have the same thing that we did before, but with the immutable data structure. And yeah, probably you're going to argue, well, this doesn't look simple, and the reality is that it's not. But it is simple. It's not easy, of course, but it's more simple. And we can simplify that by using ECMAScript 6 fat arrow functions, where we can do everything in just one line, right? So remember that old book that you have there of ECMAScript 6, go get a read there, because it allows you to do these weird things and looks quite better. So let's try with a more complex data structure here. We have an array of people where they have a name and sort of groups, and each group might have a couple of likes. So here the idea is that we want to add 50 likes, which is almost the amount of people that we have here, to the group vir in Alejandro. So to do that, we're going to create, of course, we're going to create a new list. And we're using map because we need to go through all the elements in the list in order to find the one that its name is Alejandro. Take a look at here. You are used to use map like person and do here person.name. Well, we don't have an object here, we have a map, so we need to do object.getName. So this is why I'm saying it is kind of using objects and array, but it's different. It's going to take you more time, but in the end, it's going to be much more simple than when we see the entire structure of our code. So if the person name match Alejandro, then we're going to do something. If not, we're just returning the person. Here, what we're doing, we are doing the structure sharing. If the person is not Alejandro, then the same reference, the same map is going to be in the newly created list. Then for Alejandro itself, I'm going to update only the groups part, and I'm using here again another updater function which receives the groups, that list. And for the list, I'm going to run map again against that list, and for each group, I'm going to find if the label is vir, and then for that specific group, I'm going to update the likes attribute, and then I'm going to add 50 to that. You see, we're doing quite complicated things here, but in a simple way. I know you don't believe me, but pretty sure most of them that have been working with React and Redux sometimes find yourself creating arrays and using the spread array operator, which I hate. But this is much more simple than that, and at least it is much more maintainable because it's clear what you're doing here. Probably if you write this in ECMAScript 5, you're going to have a hard time writing function and function again, but here is much more clear. So yeah, by the use of ECMAScript 6, this here is what you feel, that you are starting to do more like real computer science. Now what about React and Redux? Well, I've been talking to you about these problems that we have when we try to modify, for example, in a to-do application, we want to signalize that one to-do is done, right? If we want to modify that specific object, we can do it like this, and then we are forced to create a new array using the spread operator here, and we are slicing the older array to avoid including the index of the to-do that we are modifying, and then we're creating here another array and using the spread operator to fulfill the entire array. So here we're creating 3 arrays in order to return just a new array, right? this is not free. The spread operator takes some time to process. So if we use Immutable.js, all what we're going to do is we're going to just create an update and a specific index. We're going to receive the to-do in the updater function, and then to the to-do we're going to just set the done attribute to true, which is going to return, of course, a new to-do, which is going to save that new to-do into the new to-do array, and it's going to return that. So this is how we'll optimize React. And if we do this, we're going to be able to use the pure rendering mixing in React, which is going to improve our speed on rendering, because we're just using immutable data structures. There is a project out there, it's called It is a Clojure implementation of React, which is faster than React. How could it be faster than React if it's wrapping React in Clojure? Because every data structure in Clojure is immutable. So that's the reason which is faster than React. So I seriously encourage you to take a look at Clojure languages and immutable data structures. And if you have any question, in order to see something like that, don't feel motivated by the GIF there. It says just no questions. Redux or React, or you want to see how it works? That's it. Okay, perfect. That's all I have you for. That's all what I have for you today. So thank you. Ahora sí, le pregunté.